Hello and welcome to a new session for this online course on Introduction to Embedded System Design. I am your instructor Dhananjay Gadre, and in this session I am going to cover a very important aspect of embedded systems, which is the ability to count time, measure time, count events and so on and so forth. And the basic building block, a peripheral which is a critical peripheral in any microcontroller ecosystem, is the ability to count time without the intervention of the CPU, and such a peripheral is called timer, and oftentimes it is called counter/timer, which means it can count as well as count events as well as count time. The basic building block in a counter timer is actually a counter. Now, what is a counter? If I show you a n bit counter, and typically what you will have is n bits going out, and you would have a clock input. Maybe you also have a reset pin, so that when you assert the reset signal, all the n outputs of this counter, so this is a counter, are reset to 0. Thereafter, for the given configuration of the clock signal, every time there is a rising edge, the count will increment by 1. If this was a down counter, then it will decrement by 1. So, let us say that this is an up counter and so on. So, if from here, if the initial value before this was 0, then and if this was an up counter, the count will be 1 here and it will be 2 here. Now, whether the signals which are applied to the clock are like this or like this, here it will be 1 and it will be 2 at this point of time. This is, let us say, time, and these are the pulses that you are getting. If the frequency of the signal which is connected to the clock pin of the counter, we do not know the frequency, then we cannot say how much time has elapsed. All we can say is how many events have come, how many clock signals have come, and in such a case you are operating this building block as a counter. On the other hand, if I use the same hardware, I still have a n bit counter, n bits, and let us say it is a up counter. You have a clock signal, you have a reset signal, but now instead of an external signal which is generating some pulses, if this is connected to a oscillator, rectangular output oscillator, something like this, whose frequency is fixed, then after I assert reset on this pin, it will count these pulses, and if I query, if I am able to read these n bits and I find, let us say the count is 1350. If I find that the count is 1350, then I can also tell how much time has elapsed since the time that I reset this counter. How much time has elapsed? It is 1350 into the t oscillator, that is the period of the clock signal. Once I know this, by performing this small calculation, I would be able to estimate the time that has elapsed since the time I reset this counter. So, the basic building block in a microcontroller is a counter. If you connect the clock input of that counter to an external pin and expect external signals to be used for clocking the counter, you are maintaining a counter. On the other hand, if the clock input of this counter is derived from an internally generated clock, then, and if you know the frequency of that clock, then you would have converted this counter into a timer, and MSP 430 is immensely capable in providing various functions of this timer counter. Let us investigate what all we have. Now, why do we need timers? We can also use the program to count time. The reason why we want to use timers is that we can use the peripheral function to generate timing events. We can use them for generating delays, we can use them for creating what is called as baud rates, which we are going to cover in a serial communication lecture subsequently. Or you can use these timers, as I mentioned, for counting external events and so on. Having a dedicated hardware for performing this function frees the CPU from performing that task. You can also use a CPU. For example, one of the port pins could be connected to an external signal where you are getting pulses, and you can write a program saying, oh, if this pulse is high, wait for it to be low, once it goes low, one pulse has been received, you can count it, and so on. But if you did that, your entire CPU life is going to be spent only counting pulses. You will not be able to do any other activity at the same time. By offloading this counting business to a counter, your CPU can perform other functions and keep on finding out from the counter how many events have happened. This is what the infrastructure related to a counter and a timer on a microcontroller usually allows you to do, and MSP 430 is no exception. If you use a program to generate delays, and we have seen how we can write a delay function, again the delay function depends on the accuracy of the CPU clock, and if it is not very accurate, the delay period will not be very accurate. On the other hand, if you use a timer, you can use a external crystal oscillator like we have on MSP 430 to provide clock to the timer, and then it can generate very accurate delay periods. MSP 430 G2553 has two 16-bit timer A, and they are labeled timer 0A and timer 1A, and this is over and above the watchdog timer that it has, which can also function as a timer. The timers on MSP 430 are 16-bit counters, which means they can count from 0 to 65535, which means they can count a very large number. The timers can be used for capture and compare functions. I will come to this feature shortly, and it can also be used to generate pulse width modulated signal, which we briefly mentioned in a previous lecture. The timers can be used to generate interrupts on a timely fashion. You want to generate an interrupt every 1 second or every 100 milliseconds. You can employ a timer by appropriately programming it. It can generate very accurate interrupt events, which you can use to do some housekeeping jobs. You remember in the previous lecture we said, oh, we want to connect 4 7-segment displays and we want to multiplex them, and multiplexing requires that you refresh the display, which means one digit which was on, you have to turn it off, and after a predetermined period of time you have to turn the second digit on. Now you can do that job with the help of an interrupt generated by a timer. You can also use the timer infrastructure to measure frequency of external signals. You can use it to measure period of external pulses, and you can use it to output information on pins at predetermined intervals. So, these are the features of the timer. Here is a block diagram, and I am going to broadly tell you that any timer has actually two parts: the timer part, that is the counter part, and rest of the parts which allow you to compare the value of the timer to a predetermined value. So, that you know, okay, you started the timer from 0, I want to get a notification when the count reaches 5000. So, you are going to compare the value of the timer with a value in a register which you write 5000. Whenever that match happens, it will inform you. So, here is the 16-bit timer. This is called TAR, that means timer register, and then you have 3 compare capture channels. They are called CCR0, capture compare register 0, capture compare register 1, and capture compare register 2. So, with one timer you have 3 channels of capture and compare features. Of course, you can either capture or compare, and by choosing an appropriate function, whether you want to capture or compare. What is the meaning of capture? You want to capture the value in the timer. What is the meaning of compare? You want to compare the value of the timer register with the predetermined value stored in that compare register, and using these two compare or capture registers, you can do amazing things with the timer. For this counter, although it says it is a timer, as I mentioned, it can, the basic building block is a counter. The clock of the timer can be derived from these sources. As you see here, you can have the A clock, auxiliary clock, or you can have SM clock, and the TA clock in this case is actually a pin, which means the signal of the pin is used to clock the counter, and this feature can be used when you want to count external pulses, when you want to count external events. You may remember in one of the previous lectures I mentioned, suppose in this room we want to count how many people have entered. You can easily install a sensor which detects human presence, and when it detects a human presence, it will generate a pulse. This pulse can be connected to the TA clock pin and it will increment the timer, and you can query that timer at any given point of time after resetting it at onset, that what is the value at this point of time, and you would know how many people have entered the room. So, this is and then A clock and SM clock allows you to operate the timer in the timer mode. Why? Because A clock and SM clock are locally generated clock signals and you know the frequency of these clock generators. So, the count in the timer will tell you how much time has elapsed since the time you started the timer. Now, when do you compare and when do you capture? You can do that based on signals on the microcontroller as well as events within the microcontroller. You can use it to capture the value of the timer, or you can use it to compare the value of the timer using a value written in the comparator, and we are going to use this feature to see various activities. So, this is the basic block diagram. You have another timer. So, this is timer A0 and timer A1, and both of them have these 3 channels which allow you to do multiple things. So, the major components of a timer are a timer counter register, as we have seen, TAR. In both the timers that we have, they are all 16-bit registers, they are all read write registers. You also have a timer capture and compare register, and there are 3 capture and compare registers for each of the timer. Timer A0 CCR0, capture compare register 0, capture compare register 1, register 2 for timer 0A, and capture compare register 0, 1 and 2 for timer 1A. And both these 3 channels for say for this will use a given timer. These 3 channels will use a second timer register, and you can write values in this and you can read values from this to know whether you want to compare or you want to capture and so on. In the capture mode, the value of the timer is stored, is captured in the capture register, and you can read it thereafter. In the compare mode, you load a value in the register and wait for the timer value to reach that number. When that number is reached, some event will happen, and usually a flag will be set, or if you want, an interrupt will be generated. And these features can be used to generate pulse width modulated signal. The source of the timer can be A clock or SM clock, and you can source it from an external pin like TA clock. The clock source is selected with the help of registers in this these register bits, and once you have selected the source of clock, you can also further divide it. So, you can divide it by 1, 2, 4 or 8 and so on. These are the modes of the timer. The basic timer, that is the TAR, works in 4 modes. You can stop the timer, which means once you stop it, it will hold the value, or you can use it in the up mode, which means it will count from 0 and it will keep on counting till a highest value, but the highest value is the value in the capture compare register R0. The other second mode of operation is what is called as the continuous mode, in which it is going to go from 0, count up to the maximum count, which is FFFF, and again reset to 0 and again keep on counting. And then you have a up down mode where it goes from 0, counts up to a maximum value and decrements from the maximum value to 0 and so on and so forth. So, you see in the up count it goes like a ramp, in the continuous mode also it goes to ramp, but the value maximum value is FFFF. In the up down mode it goes like a triangle waveform. We will see this in the diagrams here. So, this is the up mode, it goes from 0, but the maximum value you set in the timer A capture compare register 0. So, the point to note is the value in capture compare register 0 is very important. That is the register which decides up to what value the timer will count. In this mode you can use it to generate interrupt at 2 times, once when it reaches this value and once when it resets to 0, when it becomes 0. So, as you see here, you have generated an interrupt here when it goes from here to here and when it is here. So, there are 2 times during this counting process when interrupts can be generated. Then you have the continuous mode, is very similar to the previous mode, except the value maximum value will be this. It will start from 0, it will go to the maximum capability of the timer, it will reset to 0, and when it resets to 0 it will generate an interrupt, as you see here. When it resets to 0 it is generating an interrupt. In the up down mode it goes from 0 to the maximum value set in this register, and once it reaches there it decrements it till it reaches 0. In this mode it is going to generate when it is just reaching that and when it is reaching 0. Okay. These are the registers associated with the timer, and I strongly recommend you to go through the data sheet to understand each of these. The best understanding will come when you write a program and play with the various features. This is the timer control register, and as you see these are the bits which allow you to turn the timer on and off. These are the bits which allow you to enable the interrupts. I recommend you again to go through these registers. This is the capture control register. These are the values, bits with which you can decide which mode of the timer, whether it is going to operate in the capture mode or the compare mode. And this is the interrupt vectors for the interrupts that will be generated because of the timer A operation. And as you see many of the interrupts are shared. Here is the interrupt for capture compare 1, this is the interrupt for capture compare 2, this is the interrupt for timer overflow for a given timer. And there are many sources of interrupts for these timers. I again very strongly recommend that you go through these slides as well as the data sheet. Now, we are going to run a little program to illustrate what can be achieved with a timer. Now, in the previous exercise we saw that we can use a delay function to toggle an LED at a certain rate. By changing the delay period you can slow down the toggling rate or you can make it fast. Here we are going to do that, except we are not just toggling a single LED, we are actually counting the count on 8 LEDs which we connected to port 1 bits. We have connected 8 LEDs, and as you see this part of the LED is grounded, all these LEDs are grounded, which means whenever this bit is 1 that LED is going to glow. Now, we are going to have a internal counter which will count from 0 to 255. When the value is 0 all the LEDs will be off, when it is 1 LED will be on, when it is 2 the first LED will turn off, the second will turn on, and so on and so forth. So, you are going to see the counter value in a binary form, but who is changing the count? The count is changing every 1 second, but that 1 second duration is not being achieved by some delay loop, and instead we have used a timer to generate an interrupt at every 1 second, and at every 1 second interval we are incrementing the count and outputting that count onto the port 1 register, so that you will see the LED is blinking or rather counting information at the rate of 1 second. There is no other interaction, there is no switch or anything like that. Once you load the program and download it and power it up, you are going to see the LEDs blinking. So, here in this program we have certain registers, we have certain subroutines. This subroutine simply determines that all the pins of port 1 should be set as output and their initial value should be set to 0. So, that when you turn on, the values will be 0. Here we are choosing the timer, various modes of timer 0. What we are doing is, we are saying that we want to generate an interrupt on capture compare register 0. The clock for the timer is A clock, and A clock is sourced from the low frequency crystal. As you know, on our MSP 430 lunchbox, there is a 32.768 kilohertz crystal. The frequency of that crystal will be used to drive this counter, drive this timer, and we want to compare when that count reaches 32768 by loading the capture counter register to 32768. When it reaches 32768, that means 32,768 pulses from the oscillator have elapsed, and since the frequency is 32.768 kilohertz, that means 1 second has elapsed. Upon that event, it will generate an interrupt. See, let us see the program. What we are doing, as we always do, this is the main void and we have disabled the watchdog timer. Now, you remember that when we were discussing about the clocks, the ACLK clock derived out of the low frequency oscillator as well as the low frequency crystal oscillator, both have to start working. They are not very fast oscillators, which means they will not start working right away after reset. It may take some time for the oscillations to build and stabilize, and to do that you have to check for this flag, as we have seen in the previous lecture. We are just repeating that code here. We are waiting in this loop to make sure that our oscillator is stable. Once that oscillator is stable, we are calling this subroutine, which we have seen previously here. Here we are feeding that A clock to the timer 0, A0, and then we are calling this subroutine to make all the bits of port 1 to be turned off. Then what we are doing? We are entering, we have loaded a value into status register to enable the global interrupt flag. This is very important. But we also have chosen to use low power 3, low power mode 3. This will disable everything except it will keep the A clock active, and since we have chosen A clock to feed the timer, which means timer will keep on working. Also the peripherals such as the ports will keep on working. So, once you execute this instruction, let me remove the comments here. Once you execute the instruction, you are going to immediately go in the low power mode 3 and you are enabling the interrupts. And before that you have already enabled the timer clock is selected from A clock. That means once 1 second gets over, you are going to go in the interrupt, and this is the interrupt program. We are saying that our vector is timer 0 A0 vector, and this is the code for it. And what is the code? Simply have a count where you are saying count is equal to increment the count. And what is count? If you see here, the count is, see, very important, count is declared as a volatile variable of the type char, which means it is a 8-bit counter and the initial value is 0. Now, volatile means whenever you increment it, it will be fetched again and again from the actual location, instead of a copy being read from any register, internal register. It will be read from memory, because this is going to be initialized in memory. So, we have declared this variable as volatile, and that variable we are incrementing, and that value, incremented value, we are simply outputting on the port 1 bits. So, once you compile, rebuild and download this program, what should you see? That every 1 second the 8 bits, 8 LEDs will start working like a binary counter, and it will keep on counting. From 0 it will reach all the LEDs are at 0, all the LEDs will be off. Then as it gets every 1 second it will increment, and at 255 seconds you will see all the LEDs on, and then in the next second all the LEDs will be off again, and this will keep on happening. And this is basically to show that the delay period of incrementing the LEDs, incrementing the count displayed on the LEDs is not being done with the help of a CPU program, with the help of a code, but it is being performed by a peripheral, which is the timer A0. And we will see more activities involving the timer, such as the capture and compare modes, and also how to use the timer in the PWM generation facility. We will see that in our subsequent lecture. I suggest that you play with this. If you want to change the frequency at the rate the clock, the count is being updated, you can go into this part of the code and change this number to a lower value, and you will see that it blinks the LEDs, it counts the LEDs faster. If you increase this, you can have a slower update. So, I suggest that you play with this code, update it, modify it, download it, and see how various changes to the code will impact the actual performance. Thank you very much. I will see you very soon. Bye bye.